Hello and welcome to Advent of Code in F Sharp Day 18. It's not day 18 for me, it's a couple of days later, but I looked at 18's problem, and when I looked at it, I was like, oh, this is the day I will use a parser library. And I started experimenting with it, and turned out that writing a parser once a year is not enough to keep it in memory, so I had to do some research. I even had to grab one of my old school books. Let me zoom in, which is called Modern Compiler Implementation, to go back to first principles even. So yeah, it was a fun day. I spent more than 30 minutes on day 18, but it was a very interesting learning experience. Day 18, operation order, it's just doing homework for the elves. But maths in Elfland works a bit differently, because if you have an expression like this, in our world, multiplication binds stronger or has higher precedence than addition. That does not apply in Elf world. In Elf world, it's just from left to right. So if we first encounter plus, we reduce the sum, and then we reduce the multiplication. And yeah, we get a lot of rules of homework, and we need to calculate the expressions, basically. So I thought, let's write a parser to parse these expressions, and let's then to an abstract syntax tree. So let's parse these to something we can work with in code a bit better than raw strings, and then just evaluate those expressions. So writing an evaluator. Part 2 is the same, but the tweak is the different operators do have different precedence levels, but it's flipped. So in Elfland, the plus binds more tightly or has higher precedence than the multiplication. So it's the other way around. In F Sharp, you have a couple of libraries, but the one I am most familiar with is called fparsec. And fparsec is, if you look at the summary, a parser combinator library for F Sharp. And you can use it to implement recursive descent text parsers for formal grammars. So that's a lot of expensive words. What does it actually mean? It means that fparsec provides like the building blocks. So it gives you functions that can parse a number, or that can parse a certain string, or that can parse whatever, like an addition sign or a multiplication sign. And next to those basic building blocks, it provides combinator functions. So it provides functions that allow you to combine parsers into like more complex parsers. So for example, you can create a parser that parses an int first, and then some white space, and then an addition or a multiplication sign. And you can like build very complex parsers using the building blocks from the library itself, or from the building blocks you build yourself based on those basic building blocks. So when I work with fparsec, it's like Lego. You build stuff and then you reuse stuff, and you end up with a very expressive way to write parsers in theory. But I had a challenge for day 18, and I want to go over it with you. So this is the code, but let's not go over it just now. If you write a parser, you need a grammar. So you need to have the rules of which the rules of production. So if you look at my type declarations here, so this is a type declaration, or a possible type declaration for the expressions we will be parsing. So this is saying, maybe start with expression. Every expression is either a value, which is just a number, or it's an operation, which is like multiplication or addition, or it's something between parentheses, and that's just saying the same thing, so it's recursive, but there's parentheses around it. And we will need this later on, yeah, because there's no precedence in the first part. And so an operation, what does that look like? It's literally a left part, a right part, and an operator. So two operands and an operator, and the operator can be a plus or a multiplication. And then what I try to do with the parser is not to compute the result, but to build an abstract syntax tree, or rather a tree structure using these types. So I transform my input strings into tree structures or these kind of things. And this is where fparsec helps. And this is actually almost the grammar. So it's saying an expression is or a value or an operation or parentheses, and you will see the same pattern emerge in the parser. So for example, if I write the rules out in, I don't know, what's it called? BNF form? I don't know. But if I write the grammar out, it's saying operator can be a plus. Oh, by the way, operator can also be a multiplication. And then for expression, the same thing. Expression can be a value. Expression can be another expression, and an operator and another expression. And expression can be whatever parenthesized, I think. But there was a problem by naively porting this to fparsec. Because if you look at this rule in the grammar, it's saying expression is expression, operator, expression. If you just feed this to fparsec, it'll go into an infinite loop because of this. There's the first thing in the parsing of an expression is parse another expression. So this will loop infinitely. So this is called a left recursive grammar, and that is not cool to work with if you're using a fparsec or something else. But there is a mechanical way to rewrite a grammar like this to a right recursive grammar. So a grammar that does not have this problem of expression being the first term in the rule for expression. And it requires a bit of tweaking, and that's why I needed the book. But there's also references online on how to rewrite the left recursive grammar to a right recursive grammar. So I will not bore you with the details. Only that I ended up with this grammar instead. So expression is a value and some other form of expression, and this some other form can be nothing. So expression can just be a value, or this special expression can use operator and another expression. So this is a rewrite of the same rules you see here. But if you look at these three rules now, there's no left recursion. So it's always something else other than an expression. And this works just fine for writing a parser or using a parser library. So if we look at the parser right now, this is where the parser definitions start. So this is actually a complete parser for the language, which is what, 13 to 30, 17 lines of code. So I find that very pleasing. It took me hours to figure out. That's the negative part. But if you look at it, it's pretty interesting. And what actually took me the most time was this left-right recursion thing, but also just relearning the library, because you see all kinds of magical operators and this operator, and then there's this really weird parser forward to ref thing. I will not bore you with the technical details because this will only be relevant if you are writing F# parsers using fparsec. But the gist of, for example, this thing is if you want to use a parser recursively, so for example, I define a parser for expressions, p expression here, and I use that in a parser for expressions itself, then you need to do this hacky thing that's totally not idiomatic F#, but you need to be able to do it because the way the parser combinator library is structured, it returns functions, not values or something else. It's a value, not a function, so it's really hard to write mutually recursive things, and this is their hack, but that's a detail. Actually, let's focus a bit on this. For example, how do we parse an operator? Well, we have these basic building blocks, so a parser that recognizes pluses, and if it's a hit, let's say, if it matches or if it parses, it'll return the add operator we define. Same for multiplication. This is basically saying OR, so this combines two parsers and returns an OR parser, so it returns either adds or mults, or it matches adds and multiplications. And this is saying, okay, and combine this parser on the left with this parser on the right, which is a match for any kind of white space. And this combined thing is saying, yes, you must match on both, but only keep the result of the left. That's why this dot is on the left of this operator. You also have them on the right and stuff, but that's it. And you do this for everything. And expression is a bit more tricky, as I said, because it's recursive, but the same principle applies. And then you just run your parser on a line of homework, and it parses everything into this structure. So then we have our abstract syntax tree. And the next step is to evaluate that expression or that tree. And that is just writing a recursive function that matches on all the cases. And the tricky part was there's no operator precedence in part 1, and in part 2 it was flipped. So let's go maybe to part 2. So the tricky part is when we are trying to evaluate an operation, we can't just do first evaluate the right and then do this plus or multiply with the left, because you need to take precedence into account. And in my abstract syntax tree representation, it came down to looking at, okay, we are evaluating an operation, let's look at the next term, and if it's another operation, then we can apply precedence rules. So that's the basic idea of it. Yeah, and that's it. It was a lot of work because I forgot everything about parsers, but once you know what you're doing, it's actually a really cool way to parse non-trivial things. So yeah, really fun puzzle for day 18. I hope you learned something, or at least know what to Google if you want to dive into it yourself. So that's fparsec and parser combinators for day 18. See you tomorrow.